You are flying clear of clouds, and in a single second, the windshield goes entirely gray. You have lost your primary visual reference to the horizon. Of all the mechanical and operational variables in aviation, weather remains the singular factor over which a pilot has zero control. To understand the stakes, we look at accident statistics from the Oxford Aviation Academy, which track the role of weather in aircraft disasters. The data shows that poor visibility is responsible for exactly 66.7% of all fatal weather-related crashes. Secondary hazards like structural icing and snow account for another 20% of fatalities, physically altering the wing and destroying lift. Because these factors are uncontrollable once airborne, safety depends entirely on a pilot's ability to anticipate them before takeoff. Meteorology provides the predictive tools necessary to recognize these lethal traps and ensure the safety of every flight. For student pilots, the primary challenge is memorizing the massive volume of disconnected facts and figures required for the DGCA exam. We will organize this invisible fluid of the sky into a single, structured spatial blueprint. This blueprint covers three core areas: the composition of atmospheric gases, the vertical temperature layers, and the standard atmospheric model. Mapping these concepts onto a physical grid provides a framework for recalling complex data under the pressure of the exam. The atmosphere is a spheroidal gaseous envelope, held against the Earth's surface by gravity, and moving with the planet at the same speed and direction. This envelope consists of 78% nitrogen, 21% oxygen, 0.93% argon, and trace carbon dioxide. Water vapor accounts for 0 to 4% of this mix, creating all weather. Note two critical gas ratios. By volume, it's 4 to 1. By weight, it is 3 to 1. Because air is compressible, gravity pulls the majority of these gases downward, crushing 80% of the atmosphere's mass into the bottom 16 kilometers. This density drop creates physiological limits, mandating the use of supplemental oxygen for any flight operating above 10,000 feet. As a pilot climbs, the sky is divided into distinct layers based on the vertical temperature profile. We begin at mean sea level at 15 degrees Celsius, air cooling as altitude increases. A pause boundary marks where temperature stops changing before reversing. This first boundary occurs at 11 kilometers at negative 56.5 degrees. These boundaries define the troposphere, stratosphere, mesosphere, and thermosphere. Understanding this temperature zigzag is essential, as the thermal profile determines which layers contain weather and which offer smooth flight conditions. Pilots focus most of their attention on the lowest layer, the troposphere, which extends from the surface up to 11 kilometers. Since this layer contains 99% of atmospheric moisture, it is the domain of clouds, precipitation, and visibility hazards. The tropopause, the ceiling of this layer, acts as an impenetrable lid on storm development, making it the most significant boundary in aviation. This boundary is not a flat line. It sits significantly higher over the equator than it does over the poles. Intense solar heating at the equator causes the air column to expand upward, physically lifting the height of the tropopause. An inversion occurs when this normal cooling trend is disrupted and temperature begins to increase with altitude. This inversion layer traps moisture and particulate matter near the ground, creating dense fog and severely restricted visibility. Calculating the height of the tropopause and recognizing the traps of inversions allow a pilot to determine the exact altitude required to clear severe weather. While almost all weather is found in the lower atmosphere, two rare cloud phenomena occur much higher and appear frequently on exams. Nacreous, or mother-of-pearl clouds, form in the stratosphere between 20 and 30 kilometers during polar winters. Noctilucent clouds are found higher still in the mesosphere between 75 and 85 kilometers and are visible after sunset during polar summers. These specific seasons and altitudes contrast sharply with the standard weather found in the troposphere. While operationally rare, pinning these exact locations on the master map secures easy marks on the DGCA meteorology test. Our master map represents a set of averages, but the real atmosphere is a chaotic fluid where pressure and temperature are constantly fluctuating. This chaos makes it impossible to calibrate sensitive pressure instruments against a baseline that never stops moving. The solution established by ICAO in 1964 is the International Standard Atmosphere, or ISA. The ISA provides a universally agreed-upon theoretical model of a perfectly average atmosphere. It establishes permanent reference values, such as a constant 15 degrees Celsius at mean sea level, that do not fluctuate. This foundational baseline ensures that an altimeter built in France reads the same standard altitude as one in India, enabling global flight planning. We have now constructed the full map, integrating atmospheric composition, thermal layers, the tropopause, and high-altitude cloud exceptions. This schematic visualizes the thermodynamic engine responsible for the lethal weather hazards pilots must avoid. Mastery of this map allows for the accurate interpretation of forecasts, METARs, and TAFs used in daily flight operations. Internalizing this blueprint enables a pilot to make sound go-no-go decisions, transforming raw meteorological theory into applied flight safety.